So now, for problem 2, it says, recall from chapter 8 that if we use the variable human body temperatures, in degrees Fahrenheit. So if we look at the data set of all human body temperatures recorded in degrees Fahrenheit, that would form a bell-shaped distribution. This was from chapter 8. So if X is bell-shaped, this is given, that means that the frequency distribution of all human body temperatures would form a bell-shaped histogram with, and this is also given, the mean, which we use for mu, the mean body temperature being 98.2 degrees, and the standard deviation of all human body temperatures being 0.6 degrees. We know from the empirical rule, this is all from chapter 8, the empirical rule for bell-shaped distribution says 68% of the data values lying in any bell-shaped distribution have to lie between mu minus sigma and mu plus sigma. That's the same as saying 68% of the data values in a bell-shaped distribution are within one standard deviation of the mean, either below the mean or above the mean. So in general, for any bell-shaped distribution, it doesn't matter what the variable is, 68% of the data values are guaranteed to lie between mu minus sigma and mu plus sigma. Well, in this case, for this distribution, we can compute mu minus sigma, mu plus sigma from the given mean and standard deviation. Mu minus sigma would mean 98.2 minus 0.6 degrees, and if you subtract 0.6 from 98.2, you get 97.6 degrees. And if you add 0.6 degrees to 98.2, you get 98.8 degrees. So for this particular variable, human body temperature, the fact that it's bell-shaped, the empirical rule guarantees that 68% of all humans have to have body temperature somewhere between 97.6 degrees and 98.8 degrees. Now, what the question says is, now, this is all given, it says, what is the probability that a randomly selected adult will have a body temperature that's somewhere between 97.6 and 98.8 degrees? And then it says, which interpretation of probability did you use to answer this question? Well, just like in problem 1, what we're given by the empirical rule is a relative frequency breakdown here. We're told that 68% of the population have this property, that their body temperature is somewhere between these two bounds. And anytime you know the relative frequency breakdown of a population for any given property, the relative frequency interpretation of probability says that the probability a randomly selected individual from that population will have that given property has to be equal to the relative frequency of individuals that have that property in the population. So the property here is the property that a randomly selected American will have a body temperature somewhere between 97.6 and 98.8. But we know that 68% of all Americans have that property. So the probability that a randomly selected adult American is, or not American, just a randomly selected human is going to have a body temperature between these two numbers is going to be equal to the relative frequency of occurrence, which as a decimal is 0.68. And of course, just like in problem 1, this is based on relative frequency. So we're using the relative frequency interpretation again, together with a fact from chapter 8 about bell-shaped distributions called the empirical rule. And so using that fact from chapter 8, the empirical rule, together with the relative frequency interpretation of probability, we can determine that there's a probability of 0.68 that any randomly selected human any randomly selected human is going to have a body temperature between 97.6 and 98.8. So the answer, 0.68 by relative frequency interpretation. Make sure that all went in there. It did. So now we're going to move on to problem 3. Remember that if you have any questions over any of the problems on this video or anything else pertaining to test 3, I will be available from 8 to 9 o'clock on the chat feature on eCourse to answer any questions that anybody has. So if there's any questions about this video or the video I did on hypothesis testing or any other questions pertaining to test 3 about anything pertaining to the materials or anything else, I will be on eCourse in the chat room Monday through Thursday of next week. So that means August 6th through August 9th, I will be on the chat on eCourse from 8 to 9 p.m. All you have to do is go on eCourse and I will be free to answer any of your questions if you have any. So anyway, so let's move on to problem 3. Here the procedure for all of these problems is, suppose you draw a single card from a sufficiently shuffled deck of 52 cards. And as we discussed in class, every procedure has a set of simple events. We call that the sample space for that procedure. It consists of all the possible outcomes for this procedure that cannot be broken into smaller event components. For example, one possible event for drawing a card from a shuffled deck of cards is you might obtain a spade. So you can look at the event that you might draw a spade. A spade, though, is not a simple event because you can further break that down into 13 more events, which would be ace of spades, 2 of spades, 3 of spades, up to king of spades. So the simple events for this particular procedure would be the actual individual cards given by both number and suit. And we call that the sample space for the underlying procedure. And in this case, that sample space would be the set consisting of the 2 of clubs. That would be one card given by both number and suit. The 3 of clubs, ... all the way until you got to what? The ace of spades. So each individual card given by both number and suit is a simple event for this procedure. And there are precisely 52 simple events for this procedure. We then say that little n is 52. Little n being the number of simple event components, simple events associated to the underlying procedure. The other thing we notice is, since we are drawing from a sufficiently shuffled deck, that then says that any one card is as likely to occur as any other card. And we have a formula on our cheat sheet, Formula 1A, and what it says is, the classical method, Formula 1A, says if each simple event has an equal likelihood of occurring, and A is an event, then the probability of A occurring is equal to the ratio S over N, where S is the number of simple event components comprising the event A. So S is the number of simple event components that you can break the event A into, divided by the total number of simple events for the underlying procedure. Well, here it says, in part A of this problem, let's just say probability of E, since we're talking about part A of the problem, let's use the event E. The event E, it says in part A, what is the probability that you will draw an ace? So if we use E to represent the event that you will draw an ace after drawing a single card from a shuffled deck, then since all simple events for this procedure are equally likely, this would be the number of simple events that led to an ace divided by the total number of simple events for the procedure. And since there are 4 different cards that lead to an ace, ace of clubs, ace of diamonds, ace of hearts, and ace of spades, S is 4. There's 4 simple event components for the event that you draw an ace. So this ratio then becomes 4 over 52. 4 aces in the deck divided by 52 possible cards in the deck. And you can either leave this as a reduced fraction, and this is not a reduced fraction since I can divide 4 out of the top and bottom. I could reduce this into lowest terms by dividing 4 out of the top and bottom, and I could leave my answer as 1 over 13. Since 4 over 52 is equal to 1 over 13 in lowest terms. Or I could what? Divide 4 divided by 52 or 1 divided by 13 and write my final answer as a decimal, rounded to 4 significant figures. And if I did it that way, I could write my answer as 1 divided by 13 on your calculator would round to 0.07692. So that's the answer written as a decimal rounded to 4 significant figures. So you could either write 1 over 13 as your answer for part A or 0.07692. Either one of those would be an acceptable answer for part A. All right, now let's go to part B. In problem 3B, we're given that it says, what's the probability that you will draw either an ace or a king? Notice then we have that or in the statement. So anytime you see either an event occurring or some other event occurring from an underlying procedure, we have a compound probability. Just like we had back in problem 1B. So we see the clue that tells us this is a compound probability is the either or part of this. So this can be written as the probability that either the event E occurs or the event F occurs, just like we had in problem 1B. The or is what makes it a compound probability. So just like before, in problem 1B, we have to decide whether to use formula 1C or formula 1D to evaluate this compound probability. So it depends on whether the events E and F are mutually exclusive events, that would be formula 1C, or E and F form non-mutually exclusive events. Well, here, E has to be the event that you draw and so it says either draw an ace or a king. So this would say that the event E is the event that you draw an ace, and the event F would be the event that you draw a king. So let's think about that. In order for E and F to be mutually exclusive events, this says it must be possible to draw a card that can be both an ace and a king at the same time. Is it possible to draw a card from a shuffled deck and end up getting both an ace and a king simultaneously? No. If you look at all the simple events that lead to an ace, and you look at all the simple events that lead to a king, there's no common simple event components between E and F. Right? So that would say that E and F are mutually exclusive events. And so we would use formula 1C. That's the general addition rule on the cheat sheet for mutually exclusive events, since E and F are mutually exclusive. So that means we'd get the probability of E plus the probability of F using formula 1C. Now, the way we're going to get the probability of E and F is, of course, the classical approach, since we know that for this procedure, all of our simple events are equally likely. So the probability for E is the probability that you'll draw an ace, and we already had that was 4 over 52.